Hello, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video, we're going to go over different reactivity considerations. So we've gone through this mechanism and we've had practice writing these out ourselves and calculating the energy changes that occur. The next step in this process is just to figure out what type of influences structurally that we can identify with in order to figure out whether a reaction is going to be favored and faster and slower and so on. So we're going to look at different structural considerations and identify patterns that emerge from these structural characteristics. Okay, so let's get started. And the first thing we're going to do is a rate determining step analysis. Now, I already mentioned to you in the previous video, the theory video, that the rate determining step is in fact P1. But I want you to be sensitive to something. Notice that when we look at this equation from top down, the initiation requires 243 kilojoules per mole. So that means that we're really going up high. Remember, if we take this as a diagram, we're going up really high, and then from here, we're going up a little bit higher to 8, and then we're going to finally drop and then drop again, right? So that's our reaction diagram. And so from here to this point, well, I should go like that, that point, that is the highest hill, that is the highest gap that you must go through, climb. So that's 243. So by looking at that, you would think that the rate determining step should be the initiation, but it's actually not. It is propagation, P1. So this is the highest hill you got to climb. If you measure it from where you begin, this hill right here is the highest point from where we begin as a reactant. That's the highest point in the diagram. Now it always works out this way. It's always going to be where the propagation 1 is the rate determining step. So you have to think about it in terms of the visualization here. You always go up higher during that P1 than you did for your initiation. So you have to really remember that in general, when you figure out the rate determining step, it's always about where you begin as a reactant and to the highest hill or the highest point, the highest transition state that you have to get through. Okay, so that's why we see that. Now, P1 is the rate determining step. Everything after that is all favored, right? It's all exothermic. But this is the most endothermic. It's the combination of 243 and 8 in this case. Okay, now, when we think about the initiation, and again, I want to just emphasize there's a pattern here that's different than what we're going to see next. Okay, so if initiation was the rate determining step, and I ask you which halogen would you expect to actually require the most energy? Well, when you do your analysis by looking at the bond dissociation energy table, you would find that fluorine is going to actually require 159 kilojoules per mole. That's when the bond breaks, that's what's absorbed, right? Whereas if you look, chlorine has the highest number, followed by bromine, followed by iodine. So well, actually followed by fluorine, then iodine. So if I put this pattern together, we would think that the one that requires the most energy is Cl. So Cl radical, to make that, is going to require it's the most endothermic, it requires the most energy, right? More so than Br radical, more so than fluorine, and more so than iodine. So this is the most endothermic, and this is the most, or I should say the least, they're all endo, the least endothermic, right? So when you look at this trend, be sensitive to the pattern. So if you had numbers, you could see, okay, well, chlorine is more endothermic than everybody else, and then bromine, then fluorine, then iodine. Get this pattern. Just, you don't have to memorize it, but I just want you to be sensitive to it. Okay, you'll see why when we go to the next page. But again, just keep in mind that initiation is not the rate determining step. Now think about it like this. We only need a very little bit of initiation, right? Initiators are not required in large concentration. A tiny bit goes a very long way, because once you make a radical, that thing is bouncing around. It's going to hit something that's then going to go through that propagation, right? The chain reaction step, where it goes to P1 and then goes to P2, and it just keeps going on and on and on. So you don't really need a lot of radical to begin. You just have to make a little bit. So even though this does require a lot of energy, more than any other step, right, in terms of the increase in energy that's going on here, it does require the most energy to do this. You have that energy from heat or from the light. When you shine the light or you put the heat in from the, putting energy from heat, that's going to give it the energy to overcome this extreme barrier to get the thing going. But once it goes, it's very fast, right? After that, it goes through P1. Now, I don't mean fast because P1 is the slowest step, but it doesn't require as much energy, right? So once you actually make this into a radical, now it doesn't require much more to go through the rest of the process. And so this is what goes on and on over and over again. And you keep making new radical. So you don't have to make a radical through this initiation anymore. You just do it a little bit, and then the propagations take care of the rest. They keep creating new radicals. Okay, so let's take a look at the next part, and then you're going to see why I'm emphasizing this trend right here. So do you need to memorize this trend? The answer is no. You don't need to memorize this, but you should be sensitive to it. Realize that this trend here, initiation trend, is very different than the trend I'm going to show you now. Okay, now this trend is about propagation 1. So when you go through P1, well, let's deal with methane again like we did in our previous video, so in our theory video. So methane is going to collide with one of these halogens that became radical. And if it's fluorine, then you make a CH3 radical and HF neutral. And look how much energy is released, negative 570. That's a lot of energy being released out into the environment. Now, what's the net result of that? Well, you're releasing negative 570, right? But you're gaining 440, so that if you subtract 570 from 440, you get 130, negative 130, right? Because there's more negative than there is positive coming in. You're releasing more than you're gaining, right? So that's how we knew it's a negative 130. Now, that's important. This is exothermic. It's weird, right? Because this is the rate determining step. Remember, the second step is the rate step, and it's exothermic. So this is important to think about in a moment. Now, methane, when again 440, you break it apart into a radical, but then you make the Cl become HCl, and so then you get a plus 8. So the numbers are very close together. It's endothermic or exo. Well, this is endo, but the truth is that this is actually exo. It's not exo in this example. This is a very small amount of endothermic change here. Now again, you see how it's 8? It's not a really big number. Now, if it was any other hydrocarbon besides methane, if it was ethane, propane, butane, anything else, it would be exothermic. So this right now is endo, but not. It's right on that fence. It's almost at the 0 mark. And it's because it's methane. Methane radical happens to be one that's not very stable. We'll come back to that in a moment. But if it was any other hydrocarbon, that would be an exothermic process. And I want you to keep that in mind, okay? You'll see why as we go on. Methane here with Br radical becomes HBr. And this here is, in fact, losing energy, right? It's a negative value on this side. But look, there's more gained, right? 440 is gained. 366 is lost. The net result is definitely, in this case, it's much larger than, it's really far away from 0, right? It's really high in energy compared to, let's say, 8, like the one right above. This is definitely endothermic, and it always will be. So it's not going to change that much when you add more carbons. It's still going to be endothermic. So this for sure is endo. This one is on the fence of endo-exo. I'm going to write that there because you're going to come back to this after we're done with this video and think about it, as we go on. Okay. Now this one here is the opposite. This here is extremely endothermic. This is a high value. It's even bigger. It's gaining more energy than the fluorine, which is extremely exothermic. So this is endothermic for sure, and it's highly endothermic, highly. And so what does this pattern tell me? What do we look at when we see this trend? What we find is the following pattern. The middle two are good to work with, okay? Because the Cl, HCl, that process there where you're making a HCl, that is exothermic if it's not methane. Right now it's endothermic, but really very small amount. Whereas Br is endothermic, but not significant compared to I. See that? So